Today we will be solving physics paper, a theory extended from March 2023. So the first question is, a boat crosses a river. The boat points at right angles to the river bank and it travels at a speed of 3.5 meter per second relative to the water. Let's assume this is the river bank and this is the direction that the boat wants to flow towards. Now it is at right angle with the river bank. So, and the next line is, a river current acts at right angles to the direction of the boat points, and the river current has a speed of 2.5 meter per second. So the current of water that is flowing is at right angles to the boat. So boat is moving, let's say, to the top with a speed of 3.5 meter per second, and the current is flowing with a speed of 2.5 meter per second. So I will just simplify it by drawing a vector diagram. So vector diagram shows the direction of the boat and the current. So this is the boat and this is the current. They are at right angles to each other, and they are also right angle with the bank. So I will just connect the tail of this vector to the head of this vector. So I will get the direction of the boat that it will go as it is being pushed by the current of the water. So it will make some angle, let's say theta. So first of all, what we want to calculate is the speed of the boat relative to the river bank. So firstly, as it is a right angle triangle, so what we can do is we can use Pythagoras theorem to solve the equation. So let's say c squared is equal to a squared plus b squared. So in this case, a squared is the speed of boat and plus b squared is the speed of the water. So next would be to find c, which will be equal to square root. So I will just write square and root of a square plus b square. So square root of a square plus b square. So in this case, a was the speed of boat and b was the speed of the river. So 3.5 squared plus 2.5 squared, and then whole square that. So the answer comes out to be 4.3 meters per second. This is the speed of the boat now relative to the river bank under the influence of the current which is flowing against it or at right angles to it. So that is the speed of boat. Next is to find the direction relative to the river bank. We will again use the same vector diagram, but now we will be concentrating on the angle that it is making. So it wanted to go straight, but due to the current of the river, it is made to go to the left. So this angle will be equal to this is the formula would be for tan theta, because we want to find the angle that it is making relative to the bank. So tan theta would be equal to, we know it is opposite upon adjacent. So in this case, opposite is 2.5. Sorry, so the angle would be here. So opposite is 3.5 and the adjacent is 2.5. Now we want to find the theta. So the formula, though you will have to arrange this formula for theta, it will be theta equals tan inverse of 3.5 divided by 2.5. So if you plug this in our calculator, we will get the angle to be about 54 or 55 degrees relative to the bank. So the speed of the boat comes out to be 4.3 and the direction comes out to be about 54 or 55 degrees relative to the river bank. Now the next question is, speed is a scalar quantity and velocity is a vector quantity. Now speed is a scalar quantity because it only tells you the value at which something is going. So in this case, boat is going at a speed of 3.5 meter per second, but due to the current of the river, it is now going at 4.3 meter per second relative to the river bank. So that is now the velocity. So 3.5 is speed and 4.3 will be the speed and 4.5 meter per second will also be the velocity of that boat. So another example for scalar quantity would be anything that you can measure with a scale basically. So a weighing scale would measure a mass, a meter ruler can measure distance. So that will be a scalar quantity. And in vector quantity, it should be something that also gives a direction along with its value. So acceleration is a vector quantity, force is a vector quantity because force is mass times acceleration. So if you multiply any scalar by a vector, you again get a vector as a result. So an example for scalar would be, let's say, distance, and for vector it could be weight or acceleration. Now moving to second question. Now second question is saying that Figure 2.1 shows a ship loaded with containers and it is traveling on seawater. The first question is, the ship is made of steel. Now, we know steel is much more denser and it is about 7,800 kilogram per meter cube. And it is floating on seawater, which has a density of about 1,000 kilogram per meter cube. Now, we know if something is much more dense than water, it will sink. But in this case, it is floating. So, the explanation for that would be, there are air gaps in the some sections of the ship, which is decreasing the average density of the whole ship. Even though we have containers on top of the steel boat, the average density comes out to be less than the average density of water. So the answer should contain that the ship is not solid steel. It is not purely made of steel. There are some gaps which are filled with air. And the next point would be, because of that air, the average density of the ship decreases and it is now less than the density of water below it. Next question is, the containers with the greatest mass are loaded near the bottom of the ship. So state and explain the effect on the stability of the ship of loading the containers in this way. So let's say this is a ship and the heavier boxes are placed in this section. The lighter are placed on top. So this is done because it will lower the center of mass of the whole ship, because as density, we can decrease the average density of the ship. We can also decrease the overall center of mass of the ship just by putting most of the mass at the bottom of the ship. So this increases stability because it is much more closer to now to the surface of water. Next question is, a crane lifts a container 48 meters vertically upwards. The mass of the container is 30,000 kilograms. Now they are asking us to calculate the energy transferred to the gravitational potential energy stored in the container. So we know the formula for GPE is equal to the mass of the object multiplied by the acceleration due to gravity, and then again multiplied by the height that the object is taken to. So this equation works because we are working against the force of gravity. So crane is lifting against the force of gravity to a height of 48 meters. So we know the mass, which is 30,000 kilograms. We will multiply it by 9.8 because that's the acceleration due to gravity on Earth, or the gravitational field strength of Earth, and the height is 48 meters. Now the units have to be precise because we are working in SI units. So the unit for height is in meters, so we don't have to change that. Unit for mass is in kilograms, so we also don't have to change it. And G is already in meters per second square. So the answer would be 30,000 multiplied by 9.8 multiplied by 48, which comes out to be 1.4 into 10 to the power 7 joules. Now, why are we writing it in powers of 10? Because it is much more easier to, because we don't want to miss any extra digit. So we write it as in the form of 10 to the power. So the other way to write it would be just to write 1.4 megajoules. So a mega is a million. So 1 kilojoule would be 1000. So another way would be to write it as 1400 kilojoules. So either one would work. So we can write it as powers of 10 or megajoules or in kilojoules. And as it is energy, that's why the unit was joules. Now, third question is, state the principle of conservation of energy. Now, principle of conservation says that the amount of energy that is present in the universe is constant. It is not changing, but it can exist in different forms or in different states. So if let's say I am providing some electrical energy to a bulb, so that electrical energy will be converted into light and heat, because light bulbs also give out heat. But the total amount of energy hasn't changed. Just the form has changed from electrical energy to light and heat. Now the next question is, a wind turbine has a maximum output power of 1.8 megawatts. The turbine operates at maximum power for 4 hours. Define the unit kilowatt hour. So formula for power is energy per unit time. So we want to arrange it for energy. So energy would be equal to power into time. So in this case, power is mentioned in kilowatts. So kilowatt, and time is mentioned in hours. So kilowatt hours. So the definition would be just energy transferred in 1 hour at a rate of 1 kilowatt. Because as there is nothing written here, so we will just assume it as 1. So 1 kilowatt is transferred every hour. Now, next question is to calculate energy produced by wind turbine operating at maximum power for 4 hours. Give your answer in kilowatt hour. So we already know the equation, which is energy is equal to power into time. So we will just plug in the values for power, which is 1.8 megawatts. So 1.8 megawatts. So we will convert this megawatt into kilowatt. So you will just have to shift the decimal place by 1000. So it will be 1800. Now multiply by 4 hours. So it comes out to be 7200 kilowatt hours. So the energy transferred in 4 hours is 7200 kilowatt. So it took 7200 kilowatt hours every 1 hour. Now the next question is radiation from the sun is the main source of energy for most of our energy resources. State 2 energy resources that are not due to the radiation from the sun. Now, as we are only talking about radiation from the sun and not effects of sun. So gravity would not be included in the answer. So only radiation part is mentioned here. So geothermal energy. Now we know geothermal energy comes from the inside of the earth or the core of the earth. So geothermal. So geo means earth and thermal means the heat generated by the earth. Another example would be nuclear. Nuclear energy comes from the bonding between the nucleons in the, let's say, a uranium atom. So it is also not influenced by the radiation from the sun. Another one would be tidal. Now, if they would have mentioned, let's say, effects from the sun, then tidal would be the answer because tides occur due to both the gravitational pull of the sun and the moon. So in this example, it will work because we are only talking about the radiation from the sun. So any two from this would be the right choice. Now moving to the fourth question. Fourth question says that figure 4.1 shows a metal pan on an electric hot plate. The pan contains 200 centimeter cube of water. The pan is heated. The temperature of water in the pan increases. So they have asked thermal energy is transferred through the metal pan by conduction. As they are touching each other, that means particles are in contact. That means conduction is taking place. State and explain the two way that thermal energy is conducted in a metal. So the main source of conduction in metal is due to free electrons, or we could say delocalized electrons. So these are electrons that are not bound to any atom. Let's say we have a pan made of copper because copper is very good conductor of heat. So it will have free electrons that are not bound to the atom of the copper. So that means they can move around easily. Now, if let's say the pan is being heated from the bottom, so the temperature will, the heat will be transferred to the top of the bottom part of the pan. So it will heat up the bottom part of the pan first, and then it will transfer the heat to the water. So in metals, one example was free electrons, and second way would be via the use of lattice vibrations. Now a lattice is just arrangement of atoms inside, let's say, a metal. So I will just draw a grid. So the points where the dots are made are the atoms of the copper. So when energy is applied to these atoms, they will start to vibrate up and down, or in any direction, it doesn't matter. But as they are connected with other atoms, they will transfer the energy to the surrounding atoms. Now they will also start to vibrate and transfer energy from the bottom of the pan to the water. So one way of transferring energy is by free electrons, which will take the heat away from the pan and add it to the water. Another way was by lattice vibration. Next question is the water boils and leaves the liquid as a gas. Explained in terms of forces and distance between particles, while the gas occupies a much greater volume than it does as a liquid. Now, an example would be, let's say we are boiling water. So if we are boiling water, the water will now transition from being a liquid now to a gas, which we call as steam. Now, as it transition from being a liquid to a gas, that means it has moved further apart from every other water molecules. So it is still water, but in the form of gas. So liquids have particles close to each other, but in gases, they are further apart. from each other. So first is the liquid is converted into gas. That means the particles have now grown further apart from each other. That means if they are growing further apart from each other, that means the attraction between the particles have also reduced. So the volume, the particles will try to take up more volume than it did when it was a liquid, because it also has more energy than a liquid. To convert from liquid to gas, you had to provide energy. So the gas has more energy than the liquid when it transitions from being liquid to a gas. Next is state two ways in which boiling differs from evaporation. So one way is, we know evaporation takes place only at the surface of the liquid, because if let's say we have a puddle on a sunny day and it is filled with water, the water will only evaporate from the surface, because the temperature, let's say at that time, is 35 degrees Celsius. It is not nowhere near close to the boiling point of water, but it still loses its molecules from the surface. So boiling happens at a fixed rate or fixed temperature. Next point would be, it happens throughout the liquid. It happens throughout the liquid. So boiling happens at a fixed temperature, and it also happens throughout the liquid. Whereas in evaporation, there is no temperature. If it is hot enough for molecules to gain enough energy to leave the surface, they will leave the surface, but it won't be boiling. Boiling happens throughout the liquid, because if let's say in the example before, or the figure drawn before, we start heating from the bottom. So the water at the bottom of the pan will heat up first and convert into steam. Now steam is less dense than water surrounding, so it will try to go upward. That's why we see bubbles coming from the bottom of the pan to the top when it is starting to boil. And it fully boils when all the molecules inside the water are at boiling temperature, which is about 100 degrees Celsius for pure water. So now next question is, the water is replaced with 200 centimeter cube of milk. So 200 centimeter cube of water is being replaced by 200 centimeter cube of milk. Now the initial temperature of milk is 220 degrees Celsius. Let's say the milk was placed on a let's say a table which was around the room temperature. So that is why it is at 20 degrees Celsius. And we also know the boiling point of milk is 95 degrees Celsius. So this is the point where milk starts to convert into vapor. Now the milk starts to boil when 60,700 joules of thermal energy has been transferred to it. So this much amount of energy is required to make it go from 20 degrees Celsius to 95 degrees Celsius. And the density of milk is 1.03 grams per centimeter cube. Now, first of all, we will notice that the units are in centimeter cube and gram. So the answer would be also grams. We will also deal with the CGS system, which is grams, centimeter, and seconds. Now we want to calculate the specific heat capacity of milk. So the equation for specific heat capacity is C, which is specific heat capacity, is equal to the energy which will be required to raise the temperature of 1 unit of mass, let's say in this case a kilogram, and by a temperature of by some temperature, let's say T. Just like by some temperature T, we call it theta. So specific heat is energy required to raise the temperature of 1 kilogram of mass by 1 degree. So we want to find the specific heat capacity, but to find specific heat capacity, we should know the mass, but they have given us the density and the volume. So we first of all, we know density is equal to mass divided by the volume. So mass would be equal to density, let's say small d, multiplied by the volume. So it will be equal to, density is 1.03 grams per centimeter cube multiplied by 200 centimeter cube. Now, as we are multiplying these two values, we can cancel out the centimeter cube and centimeter cube, which only leaves us with 1.03 multiplied by 200. So the final answer would be, mass will be equal to 206, let's say, grams. Now, as we know mass, we can find the specific capacity. So C will be now equal to, energy supplied was 60,700 joules. It will be divided by 206 grams. Let's put this in a bracket. Multiplied by the temperature difference. So temperature difference is 95 minus 20. So 95 minus 20. 60,700 divided by 206 multiplied by 95 minus 20, which is 75. So C comes out to be now 3.93. Now the unit would be, as energy is in joules, so we will write joules, capital J, divided by, the mass was in grams, so we will write G, multiply by the temperature was in Celsius. So we will just write degree Celsius. The unit will be joules per gram multiplied by degree Celsius temperature. So specific heat comes out to be 3.9 joules per gram into degree Celsius. We can also convert it into kilogram, just multiply it by 1000, because conversion of 1 kilogram is equal to 1000 grams. So we will have to just multiply the divided by multiplied by 1000, and you will get 3930 joules per kilogram into degree Celsius. Now next question is figure 5.1 shows a semicircular transparent plastic block. Now this is plastic block, but it is semicircular in nature. So the surface is curved and it is also straight at one section. So the ray of light is incident normally on a curved surface of the block. The refractive index of plastic is 1.5. Now it is hitting with an angle of 0 because it is incident normally. So it will go straight through this block. Now first question is calculate the critical angle for plastic. Now to find critical angle, we need to know the refractive index, which is denoted by n, which would be equal to 1 divided by sine of angle C. Now in this case, C is the critical angle, sine is the angle multiply to convert it into, and the n is the refractive index. So we will now arrange this equation to find C, which is critical angle. So C will be equal to sine inverse of 1 divided by n. So if you, let's say, multiply this sine on the left side, so it will be now sine inverse. So the equation is now C equals sine inverse of 1 upon n. So C will be now equal to sine inverse of 1 divided by 1.5. Now the final answer will be about 42 degrees. To say 42 degrees will be the angle of critical angle for this light, which is being incident on a plastic block of refractive index 1.5. Next question is draw the path of the ray in the block and after the ray images from the block. So there are two parts of this question. Draw the path of the ray in the block and after the ray images from the block. So first part is the ray going inside the block. So it will be going straight through and it will hit the straight edge. Now it is now making an angle of, let's say, 42 with respect to the normal. We'll just draw a normal. This angle is 42 degrees. So it will again bounce back or reflect with the same angle and then leave the block straight. So this angle will also be 42 because angle of reflection, law of reflection is angle of incidence is equal to the angle of reflection. So next question is figure 5.2 is a full scale diagram of a lens and an object O. So object is placed here. This is a lens and this is the focal point of the lens. So this is where all the rays which are moving parallel to the lens will meet. All the rays that meet at a point is where the focus is for this lens. So first is to determine the focal length. So to measure the focal length, we just have to measure the length between the focal point and the center of the lens. So this would be the focal length, Fm. Now next question is on figure 5.2, draw two rays from the object to locate the image, label the image. Now as we have been given the object, it is placed between the focal point and the lens. So first of all, we will draw a line which goes straight through the center of the lens. Then we will draw a ray which is parallel to the principal axis. So this middle line is called the principal axis. So it will be parallel to the principal axis. It will move towards the lens, and when it hits the center of the lens, it will go towards the focal point. So now we know the distance between the focal point and the lens. We will take the same distance from on the right side, and let's say it comes out to be somewhere over here. So it will move toward the focal point here. F. Now as we can see, the rays came from the object. So light was incident on this object. It started to go towards the lens, and then it went this way. But they are not meeting on this side. So we will draw virtual lines using the lens. So the angle that it is making with the lens will be this much, and the ray which went straight through the lens will also be carried on at the opposite side. So let's say it meets somewhere over here. So we will now draw a straight line and then label this as the image. Now we can also see that the object is much more smaller than the image. So we can use this lens as a magnifying lens to magnify the object so we can see it better. Let's say. So this was the ray diagram for question number B2. Now next question is figure 5.3 shows a simplified diagram of an eye with rays from a distant object and the path the ray inside the ray eye of a person with a short sight. So this eyeball has a condition which is called short sightedness, in which the rays meet at the focal point which is before the retina. So retina is the part where the image is formed, which takes the signal back to our brain. So the image is found before the retina. So we might be able to see only a blur image. So to fix this, what we can use is, instead of using a convex lens which focuses the point, which our lenses already do, we will use a diverging lens, which does the opposite of a convex lens. So this is a diverging lens. So the rays that will pass through this diverging lens, which are parallel, will start to go slightly apart from each other. We don't want them to go very apart from each other, just slightly, so that it meets the retina. So we will first draw the line which goes towards the retina, and then we will stretch the line now towards the retina, the other two rays. So it will meet at the retina. Now this is the fix for short sightedness. We just have to use a diverging lens which will make the focal point slightly towards away from the lens and toward the retina. So when it hits the retina, that is where the focal point would be. Now the next question is sixth one. Sound waves have compressions and rarefactions. Explain what is meant by compression and rarefactions. So compressions are regions in space, let's say in air, where particles of air are much more closer to each other, and rarefactions are regions in space where particles are much more farther apart from each other. So let's say normally the particles are this close to each other. So when they are much more closer, that's when compression happens. When they are much more farther apart from each other, that's when rarefaction happens. So as air particles are much more closer to each other, that means the pressure has also increased, because now particles are also colliding with other air particles. But in rarefaction, they are much more farther apart, so pressure is decreased. So the answer would be, for compression, it would be region where particles are closer to each other than normal, which we drew here, and also where the pressure is greatest. In rarefaction, it will be opposite. The region of space where particles are much more farther apart from each other, and the pressure is lower than normal. Next question is, we can see light from the sun, but we cannot hear any sound from it. State the reason for this. So reasons for this would be, light doesn't require any medium to travel. Light doesn't require medium travel, but sound does. So we can see the light, but we can't hear the sound from the sun. So light doesn't require a medium to travel, but sound does. So we can see the light, but we can't hear the sound from the sun. If sound didn't require a medium, we would be hearing the explosions that are happening in the sun every second. Now next question is, during a thunderstorm, an observer sees the lightning almost immediately, but hears the sound of the thunder several seconds later. So the thunderstorm is happening, we can see the light, but as light is faster than sound, we hear the thunder several seconds later. The thunder and lightning are produced at the same time. Let's say the sound of the thunder is heard 9 seconds after the lightning is seen. The speed of sound in air is 340 meters per second. Calculate the distance from the thunderstorm to the observer. Now they have given us the speed of sound in air. They have also given when we will hear the sound from the thunder. It will be about 9 seconds after the lightning strikes. So the equation for speed is distance divided by the time taken to travel that distance. So arranging this for distance, let's say capital D, it will be equal to speed multiplied by the time, which is equal to 340 multiplied by 9 seconds. So which comes out to be, in meters it would be 3100 meters, or if you want to write it in kilometers, it would be 3.1 kilometers. We just have to divide the meter by 1000, because the factor to rate of conversion of kilometer to meter is of about 1000. So 1 kilometer is about 1000 meters. So we were given in meters, so we will get the answer in meters. But if you want to write it in kilometers, just convert it by dividing it by 1000. So now next question is, in a lightning strike, there is a current of 3 into 10 to the power 4 amps. So this means after 3 there are 4 zeros. So it is 30000. So 30,000 amps for 48 milliseconds. Now this M stands for milliseconds. So for 48 milliseconds, a current of 3 into 10 to the power 4 amps is passing from the cloud to, let's say, the surface of Earth. Now equation for current is, now the definition for current is the amount of charge that is flowing through, let's say, a point in some time. So we know charge, we want to find charge, we know the current, and we know the time. So we will arrange it for charge, which will be equal to Q equals I into E. Now current is in amps, so we don't have to convert it. So 3.0, let's just write 30,000. Now time is in milliseconds. Now the conversion of 1 millisecond to a second is, sorry, let's say I have 1 second, so it will be about 100 milliseconds. So I just have to divide it by 100. So it will be 2 decimals before 48. So it will be 0.48 seconds. And this is in amps. So I will just see conversion, which is 1 second is equal to 1000 milliseconds. So we converted it by shifting the decimal. So it comes out to be, I will just write it in powers of 10. So Q would be equal to 30,000 multiplied by 0.048. So 1, 2, 3. So 3 decimals are shifted. So we get 0.048. So Q would be now equal to 1400. And the unit for charge is coulombs, capital C. So the answer for charge is 1400 coulombs. Next question is, we have to define potential difference. So potential difference, first of all, it is measured. Let's say this is a resistor of any value. You want to measure the potential difference between this point where the current enters and this point where the current exits the resistance. So we will attach a voltmeter, which will measure the potential difference across the resistor. So the definition for potential difference is work done by charge per unit. So work done by the charge to pass through a component per unit time it took to pass through that component. So work done by charge per unit time. The definition for potential difference, or another way would be to say potential work done in passing through a component in certain amount of time. Now second question is, state the equation which defines electromotive force. So difference between electromotive force or EMF and potential difference is measure of the voltage which is used up by the resistor, and this is the energy that is gained by the electrons, because electrons are the ones carrying the energy. So definition, or in this case equation of electromotive force E would be equal to work done W divided by time. So in this case it is work done on charge instead of by charge, which was in potential difference. So this is the equation which we will use in the third question, which is the EMF of a battery is 9 volts. The battery is in a circuit. Calculate the work done by the battery when it moves a charge of 30 C around a complete circuit. So we have been given the voltage and we have been given the charge. We want to find the work done. Now the equation for energy is, EMF is work done per unit time. So so the equation is actually energy, which is equal to work done per unit charge, not time. So if you mention time, then you get power. So we want to find energy, so it will be work done upon charge. So it will also be the same here. So electromotive force will also be defined by work done upon charge, and in potential difference it will be work done by charge per unit charge. So instead of per unit time, it will be per unit charge. So now using this equation, we will convert it to find W, which is equal to E multiplied by charge. So E is, in this case, EMF is 9 and charge is 30. So work done comes out to be 270, and the unit will be joules, because work done is basically energy transfer. So as it is energy transfer, so its unit would also be for energy. Now next question is, a circuit consists of a DC power supply, a lamp and a thermistor. Draw a circuit diagram of these components connected in series. So you have to connect these three components in series. So first of all, I will draw the power supply. So it is a DC power supply. So it is not battery or cell. So we will use the denotation for DC power supply, which is, let's say this is positive and this is negative. And we want to connect it to a lamp which also has a thermistor in the circuit. So let's just draw the thermistor first. Let's say we are drawing the thermistor here. and the symbol for thermistor is, let's say this. So a slash with a straight line below the symbol. So this is a thermistor, and we will now continue with the lamp. So this is the symbol for lamp, and I will just close the circuit using this. So they didn't ask us to draw a switch, so we are not using a switch, but normally we would also draw a switch. So this is the DC power supply, this is the thermistor, and this is the lamp, and they are all in series because there is only one wire connecting these two with the power supply. Now the next question is, explain what happens in the circuit you have drawn in C1, which was series, when the temperature of the thermistor is increased. Now when temperature of a thermistor is increased, and we are assuming that the thermistor is NTC. NTC means negative temperature coefficient. So negative temperature coefficient thermistor acts by decreasing the or increasing the resistance when temperature is decreased or increased. So when temperature increases, the resistance of the thermistor decreases. So it is inversely proportional to the temperature decreases. So due to this, more current will flow in the circuit, and the lamp will glow brighter if it was already on. If it was not on, it will now turn on. So, and as more current is passing, so there will be a greater potential difference across the lamp. So this is the answer. So when temperature increases, the resistance of the thermistor decreases. Because of this, more current will flow in the circuit, and the lamp will glow brighter or turn on. And due to this, there will be a greater PD across the lamp. There will be a greater potential difference across the lamp. That means more voltage is being passed through the lamp, or lamp is taking more voltage or energy to turn on or glow brighter. Question number 8 is, figure 8.1 shows a horizontal flat coil in a magnetic field. So in this diagram, there is a battery. This is the positive side and this is the negative side. This is a north and south. So the magnetic field lines go from north to south. This is the arrow. So this is the current. So we know current flows from positive to negative. So arrows will be here. So now they want us to determine the direction of the movement of the side AB relative to the plane of coil. So we are just using the plane of coil as a reference, and we will say this side will go up or this side will go down, first of all. So in this case, we will use Fleming's left hand rule, because as there is a battery attached to it, that means this is a motor, and for motor we use Fleming's left hand rule. So Fleming's left hand rule has 3 parts to it. So one is the x-axis. Let's say this is the middle finger, which is for current. Let's say, and y-axis for force, and a z-axis for the magnetic field. Magnetic field. So the thumb will be the force, the index finger will be the current, and the magnetic field would be the magnetic field will be the index current, and index field and the current would be the middle finger. So using the information of Fleming's left hand rule, which only works when the magnetic field and the direction of current are perpendicular to each other. When they are perpendicular to each other, there will be some force acting, and in this case, current is going from the battery, let's say from A to B. So direction is towards top, and magnetic field direction is towards from left to right. So the force would be in this case downwards. So the direction of movement will be downwards, or you can also write the whole coil will move anti-clockwise, because as if this is going downwards, this will move upwards, so this will start to rotate in anti-clockwise fashion. Next is explain how you determine the direction. So as I already said, we are using Fleming's left hand rule, in which all 3 quantities, the force generated due to the magnetic field and the current, are all mutually perpendicular to each other. That means they are all 90 degrees to each other. And we will also mention that the magnetic field is from north to south, which is from left to right, and the current is from positive to negative. So in this case, it will be from A to B. That's why the force is towards the downward direction. Next question: state and explain what happens to the coil as it reaches the vertical position. So now this is now moved downwards, and this side is moved upwards. So there will be a point where it will be parallel to the magnetic field, let's say, or vertical to the plane. So in that case, as we have not used a commutator, there is no commutator to switch the direction of the current. So it will now decrease when it moves towards the top, the turning effect decreases, and at the vertical position, it might stop or just vibrate back and forth. So at the vertical position, the turning effect will start to decrease or even become zero, and that is where the coil will start to vibrate. And the next question is, to operate a motor, a split ring commutator and a brush is added. So in this diagram, there is no brush and there is no commutator. So when we add it, we have now a motor added to the part shown in figure 8.1. Explain the effects of the split ring commutator and the brush on the action of motor. So we are adding the commutator just to change the direction of the magnetic field. We just want current. We want the current to flow in just one direction, from let's say left to right, which is the positive, and the right is the negative. We don't want the battery itself to change the direction. So the brush will make sure that the positive and the negative terminals stay where they are. Only the coil, the current flowing in the coil is changed. So due to that, the coil will keep on rotating in anti-clockwise direction or clockwise direction, whatever direction it was already moving. So it won't stop at whenever it was in vertical position when we didn't add any commutator or brush. So the brush ensures that the direction of current is ensured to be in just one direction, and the coil rotates in just one direction or in the same direction, and the commutator makes sure that the rotation is also smooth and continuous without getting the wire entangled. So as only the coil part of the motor is moving and not the other component like the brushes and the battery, so the chances of entangling the wires that coming from the battery is zero. Now, ninth question. A nuclear power station has a reactor where controlled nuclear fission of uranium-235. So 235 is the nuclear number for this uranium atom. Takes place. So explain what is meant by nuclear fission. So nuclear fission is splitting of an atom as it is unstable in nature. So uranium-235 is unstable in nature. So it will split. By due to this, the energy of the uranium atom will decrease. That means it will now become stable. But the process of splitting changes the element from uranium to some other element. Let's say in this case, krypton and barium. So splitting of an atom, as it is unstable in nature, it is done by bombarding the atom with neutrons. So neutrons will be bombarded on the atom, and when it hits the atom, which will split the atom and boil off extra neutrons in the process. So this will create a chain reaction. Now, as we have only used one neutron, now after splitting there are now three neutrons, one which was given earlier and two coming from the uranium itself. So it will now move to other uranium atom, it will hit the other uranium atom. Now chain reaction will take place. Now we have nuclear fission happening throughout the, let's say, a uranium ore or a block of uranium. So when it splits, so due to splitting, large amount of energy is released. So firstly, splitting of an atom, as it is unstable in nature, by bombarding the atom with neutrons, which will split the atom and boil off the extra neutrons, which will again hit the other uranium atoms, and due to this, the splitting, the large amount of energy is released. And as uranium is splitting, that means the nuclear number will decrease, and it will split into two other daughter nucleus, let's say a krypton and a barium. So they are both lighter than the uranium. Now state one advantage and one disadvantage of generating electrical power in nuclear power stations compared with electrical power generated using wind turbines. So one advantage would be, as it is nuclear, so where it is readily available, not readily available, it is continuous supply of energy. So whenever we want more energy, we can produce more just by using more uranium, or if we don't want it, we can stop it. So continuous supply of energy, and it is not also affected by weather, but wind turbines are affected by weather. Let's say there is no wind, there will be no movement in the wind turbine, so it is unreliable because if there is no wind, there will be no turning of wind turbines and there will be no generation of electricity. But in this case, they have asked the disadvantage of nuclear power station. So nuclear power station disadvantage is there is a risk of leak of radiation, which has also happened in the past. So there is a risk of leak of radiation. Next is it is costly to we have to build a whole power station just to boil some water, which will give us some energy. But that boiling is done using nuclear energy. So it is costly. There is a risk of radiation. Resources are finite. So we have to dig up uranium and then refine it. So they are much more expensive. So it is also expensive compared to wind turbines. But the advantage outweigh the disadvantage. That's why we have nuclear power plants. Next is deuterium is an isotope of hydrogen with one proton and one neutron. Nuclear fusion occurs when two nuclei of deuterium combine. An isotope of helium and a neutron are formed. Use nuclide notation to write down the nuclide equation for this reaction. So nuclide notation is, let's say this is X, the symbol for an element. A is the nuclear number, which is proton plus neutron, amount of proton plus amount of neutron, and then there is Z, which is proton number. So in this case, we are using isotope of hydrogen, let's say deuterium. So it is still hydrogen, so H. There is still one proton, but there is one more neutron. Normally, hydrogen doesn't have a neutron, but as this is an isotope, it has an extra neutron. So it will be 1 plus 1, which is 2. So 1 proton plus 1 neutron, 2. And we are using 2 atoms of deuterium, so 2 nuclei of deuterium. So we are only dealing with the nucleus part. We are not dealing with the electrons orbiting. So it will now give you an isotope of helium. Now helium is normally 4 and 2. 2 protons and 2 neutrons. That's why it is 4. But as it is an isotope, and also there is one more neutron being formed, so we will decrease the nuclear number by 1, so it will now give you 3. So that means 2 protons and 1 neutron. So that extra neutron was emitted out. We will write in the position of proton 0, because as this is a neutron, there is no proton, but the nuclear number considers a neutron, so we will write 1. So this is the nuclear notation for 2 deuterium atom producing a isotope of helium and an extra neutron. So this is nuclear fusion. So in this case, 2 lighter elements, which is deuterium, is combined to form one heavy element, which is helium, and this is what happens inside of a sun on the. Now next question is the time taken for Mars to orbit the sun is 690 Earth days. The average orbital radius of Mars is 2.28 into 10 to the power 8 kilometers, and an Earth day is about 24 hours. So we want to find the average orbital speed of Mars in kilometers per second. So as they have asked us in seconds, we will have to convert the 690 into seconds. So first of all, we will convert the time from 690 days to seconds. So first of all, we will write days, then multiply it by 24, which is hours. So after hours, it comes to minutes. So minute is 60, and then to seconds, which is 60. So this gives us some number, which is about 59,616,000 seconds. And next is we know the equation for orbital well speed. So we will denote it by v, which is equal to 2, and just write pi r, which is the radius, divided by the time period or the orbital time. So orbital time is 59,616,000, and the average orbital radius is 2 pi. Sorry, the orbit is 2 pi r. So we are using 2 pi r because we know speed is equal to distance upon time. Now in this case, distance is not just a straight line; it is revolving around our sun. So it is now, let's say, assuming that it is forming a perfect sphere, we are using the circumference of the sphere or circle in this case. So 2 pi r upon orbital speed. So we want to find the average speed. So v will be equal to 2 into, let's say, 3.14, which is pi, into the orbital radius, which is about 2.28, into 10 to the power 8 kilometers. So it is now in kilometers, and we have converted the time from days to seconds. So we will just divide this whole by this value. So 2 into 10 to 3 into 3.14 into 2 into 2.28 into 10 to the power 8 divided by the time that we calculated. So this gives us the value of v is equal to 24 kilometers per second. So this is the average orbital speed of Mars. So we are calculating based on the assumption that this orbit is a perfect circle, and that the speed is in kilometers per second. So in kilometers per second, it will be about 24. So every point where we measure the speed, it will be about 25. The average would be 24. Next is state the shape of the orbits of the planets. Now, as I already said, we are assuming that it is circle, but we know it is not actually a perfect circle. So let's say this is a sun, this is Mars. So it will have an orbit which is elliptical in nature. And right now, what is that? It will be elliptical in nature. So the sun is not at the center, where it could be if it was a perfect circle, but it is shifted towards a foci. We call this as a foci. One of the foci. It could be here or it could be here. So when it goes towards the sun, it starts to accelerate, and when it goes away from the sun, it starts to slow down. So there is a change in speed. That's why we are only interested in average speed. So as the shape is much more elliptical, we will write the answer as elliptical or an ellipse. Elliptical or an ellipse. Next question is light from distant galaxies redshifted. Now, redshifted would mean, let's say the galaxy is emitting white light because white light is produced from the stars. So stars are emitting white light. It is now traveling through space. Now, as it moves through space, the space itself is expanding. So the wavelength will become longer and longer and longer. So let's say when it reaches our Earth, it is now in the range of, let's say, about 700 nanometers. This is the range of red light. So we will see the white light that came from the distant galaxy to be shifted towards the red. Let's say it is now fully red, so it will be red shifted and the galaxy will look red in color. So this is due to the space itself expanding. So light has to travel through space. So if space is expanding, the wavelength of light will also expand. So if wavelength decreases, you will get red light. So that is what is meant by redshift. So redshift is the shift of wavelength or increasing of wavelength of light which comes from the distant galaxies. It occurs when galaxies are moving away from each other. Now, as space is expanding, let's say this is our Earth and this is where the galaxy is. So the distance between us and the galaxy will start to increase because the distance between the space between us is also expanding. So the light is expanding and the space is also space is expanding. That's why the light is shifted toward the red. So this means the galaxy is moving farther apart from the Earth. So this will give us the value of how much far apart this galaxy is right now. Next question is the last one. State the quantity that the redshift of a galaxy is used to calculate. So quantity that the redshift calculates is the speed, and much more precisely it should be velocity because there is a direction associated to the galaxy which is moving away from Earth. So speed or velocity that galaxy is moving away from the Earth. So this gives us the value of speed at which the galaxy is moving away from the Earth. So our reference point is Earth. We are stationary according to us, and the rest of the universe around us is moving away from us. So if it is much more redshifted, that means it is much more farther apart, and that also means it is moving at a much more faster rate. So that was the solution for all the questions for Feb March 2023 physics theory action paper.